Team 2205 is working alongside R&D Dynamics to help create a current sensing solution for a high-speed permanent magnet synchronous motor. The motor uses position sensorless control, which requires high accuracy from the current sensing circuitry. The PCB pictured is the top side of our current sensing solution. The 6 red squares contain the 6 individual current sensing circuits that are to be tested. Cost, complexity, footprint, and accuracy are all factors that will be measured during these tests and will determine the ranking of each of the circuits. The 3 colored squares show the 3 phases of the motor that the current sensors are connected to. The current sensors are connected in line with the motor. For a motor circuit, inline sensing occurs directly between pulse width modulated signals from the MOSFETs in the blue square and the motor in the red square. This connection style was used for our test board mainly to keep the current sensor's phase angle identical to the phase angle of the tested current. We arrived at the following 3 current sensing IC to be used on our PCB. The ACS 756 was chosen for its large allowable ampacity and its fast simulator response time. The blue wave represents the current flowing through the motor at 2 kHz, and the green wave represents the response at the output of the ACS 756. The TMCS 1101A1 was chosen due to its incredibly small design, along with its ability to survive the high currents flowing through its pins. A Kelvin resistor placed in line with the motor was used to send a signal to the OP07 op-amp, providing us with a triangular output shown in green. Since a triangular wave was used as the source voltage for the system, it appears that this op-amp design is measuring voltage instead of current as is required. Analog to digital conversion performed by ADCs is the final step for our current sensor outputs on the PCB. The chart here goes over the key advantages and limitations of the 2 types of ADCs, both SAR and delta sigma. We have set up circuits using both types of ADCs to ensure fair testing for all types of solutions. Ultium was used to design the PCB. Careful routing of the wiring was necessary to help reduce noise in the system, along with carefully placed capacitors on the 5-volt VCC inputs to help reduce any rippling effects that the current sensing IC would be sensitive to. The schematic shown is for the ACS 756, but can be used to show some of the techniques that were used on all 6 circuits. Here, you can see the capacitors used to help reduce the voltage ripple seen on the 5-volt bus bar of the PCB. This is important due to the outputs of both the current sensing IC and the ADCs relying on the 5-volt input as a reference for the output signal. If the 5-volt input happens to ripple, the outputs of these devices will ripple as well. A low-pass filter is being used to reduce lower frequency noise before the signal is sent to the ADC. A resistor circuit is set to allow the differential input pins of the AMC 1336 delta sigma ADC to read the voltage from the current sensing IC. For lower noise from the 20 kilo ohm resistor connection, a sense resistor was used. To achieve a matched impedance on the input pins of the ADC, 2 10 ohm precision resistors were used. The following circuits all employ similar techniques to achieve a low noise output. This is the circuit for the TMCS 1101A1. And this is the circuit for the Kelvin resistor in the OP07 op-amp. A protoboard was used to place components and connect the current sensor voltage outputs to an oscilloscope. Here is the setup for the ACS 756 circuit. Alligator clips were used to connect the A phase of the 3-phase motor to the current sensor, and the white wires going off screen to the right connect to a 5-volt source and a digital ground. As expected from our simulations, the latency of the ACS 756 is low. The noise is an issue here, but is also to be expected due to the nature of using alligator clips and a protoboard for a high frequency signal. For our PCB testing, we expect the noise will drop due to better wire routing and a cleaner connection between the high voltage wires and the inputs of the current sensing IC. Similar to the ACS 756 test board is our test board for the TMCS 1101A1. The twisted pairs of white wires were used to connect the A phase of the motor to the current sensor as the input pins were too small for the alligator clips. The additional 2 white wires are used to receive 5 volts in digital ground. The TMCS is shown here to be oscillating at the same speed of the motor, proving its small size can still handle the high voltage and frequency of the motor. As with the ACS 756, noise is a major issue with the design. We believe that this noise will be reduced along with the ACS 756 once tested on the PCB. To conclude this video, I will reiterate our main points and continued scheduling. The current sensing PCB has been built and will be tested the week of April 11th, when the rest of our parts are delivered. We are testing the motor current in line with the PWM motor controller and the motor itself. This will allow the current sensors to output a voltage that is in phase with the input current. To survive the test conditions of an inline setup, it was necessary to source current sensing IC that could handle the high voltages and amperages that the three-phase motor requires. While our protoboard testing was successful in showing the current sensing IC's ability to work in the required conditions, there was too much noise to call it completely successful. Due to the noise reduction techniques employed on the PCB, we believe our next round of testing will show an overall improvement to the data we have already gathered.